In the last class, we just played with the definition of vector space, and I hope at least the definition is clear to all of you now. So, what was a vector space? We call V, so this is the definition of a vector space V. Please, we haven't yet started the class, so I think there will be little doubt to ask you the friends. So if you have any doubt, just ask me. I'll be happy to answer. As you saw in the last class, we spent the entire class just describing the definition of vector space. A vector space V over a field is just an abelian group V that is closed under scalar multiplication with scalar multiplication by the elements of F. So it's an abelian group, it's closed under addition, and abelian group means that the group law you can know by addition, and then what else? So you will have these properties like associativity, identity, inverse, and for the scalar multiplication you will have also the associativity, identity. That is, if you multiply with the identity element from F, it's just the identity operation, and then distributed. Distributed in two ways. Like you have two elements of F that multiplied with the vector V, you will get AB plus BB, and then you can have also V1 plus V2, two elements of the vector space times some A. That will give you AV1 plus AV2. Okay, yeah.
Can these be not reduced?
Which one?
These two.
These two? Reduced from where?
From the properties of the space.
No, distributivity is mentioned separate. So it's one of the axioms. That is, once you have the first one is associativity that we have, that is A times B times V is AB times B. The first one. The second one is that IF, that is okay, just write 1F, that is 1 in the field A, times B is B, and the third is this property. This is a full axiom, and this cannot be deduced from these two. Alright, so let's see some examples. The easiest example is perhaps the easiest conceptual example. Of course, any field F is okay. Maybe we start with that example, in fact. So the first example is take a field R. Take a field. Yeah, field of real numbers. Field of real numbers itself is a vector. Any field actually is a vector space over itself, because so suppose we take F as our vector space V over the field F, that is the scalar multiplication is defined also from F. You know that F is an abelian group, right? A field is a group in two ways. Well, not exactly. A field is an abelian group, but if you throw a zero from this, that is also a multiplicative group. Yeah? So, in particular, take the whole of it. Yeah?
Multiplicative group.
Multiplicative group. Yeah. What? So, if what is the definition of a field? It's an abelian group under one of the operations. Yes. So, field has two kinds of operations, right? Plus and multiplication. Whatever is there, the star we call it multiplication. So an abelian group under addition and an abelian group as well. Well, and here, which one is an abelian group under addition? That is F. So field F, that is an abelian group under addition, and also if you throw away 0 from there, you denote it F by F star. This will be defined as F minus 0, set minus 0, that is we are throwing away this element from here, and this is also an abelian group under multiplication.
So, but commutativity in plus is vanished.
Which one?
You say that if an abelian group under plus.
F is an abelian group under plus,
Okay.
right? And F star is an abelian group under multiplication. And here, the identity is not 0, but 1, the multiplier. Okay. So here the identity element is the additive identity. You can, if there is any confusion on the which field you are talking about, so you can denote the sub S here, and here the identity element is 1 in the field S. So for example, if you take R here, then it is the set of the R is an abelian group under addition, and if you throw 0 from R, then R star is also an abelian group, but this time under multiplication. So take any non-zero real number, take its reciprocal, multiply it with that is but take R and take 1 by R, multiply them, you get 1 by R. Okay? And here you are in particular assuming that R is not equal to 0 because you are considering 1 by R. Okay? Yeah. So this is, a field is a group in these two methods, and then note that in particular it satisfies very easily the first condition, that is, it's an abelian group. Okay? Second is, it is closed under scalar multiplication. It is, of course, because if F star, we do not even require here that F star is a multiplicative group. All we care about that it is closed under multiplication with F. Okay? And it is because F is closed under multiplication by elements from itself. Okay? So in particular, we have that any field is a vector space over itself, be it R, be it C, be it some other more complicated field. Okay, so this was our first example. Now the second one. So now perhaps you can tell me whether C is a vector space over R. C is the complex numbers, and R the real numbers. The question is that we said that any field is a vector space over itself. So in particular, that means R is a vector space over itself. That is over R. Okay. The question is that whether C is a vector space over R. Question is C the set of complex numbers a vector space over R? What do you think?
Yes.
Yes, because C at first is a field. Okay? So C plus is an abelian group. The first condition is satisfied. Now, how about scalar multiplication? Of course, C is closed under multiplication from R, and the other properties that we wrote down, like distributivity and identity, all are satisfied. Multiply any complex number with an element, with 1 from R to get that complex number back. Right? So indeed, C is a vector space over R. Yes. Okay. How about the converse? Is R a vector space over C?
No.
Why not?
Not closed under scalar.
Very good. It is an abelian group under addition, of course. But the second condition, that is the scalar multiplication, is not satisfied because a complex number times a real number may not be a real number. Okay. So the converse, okay, but R is not a vector space over C. Okay. So here's another example that we can draw. Okay. So this was our first example, this was our second example, and this will be now our third example. That is R2 over R. This is the vector space V, and this is our field F. Okay. That means in this field, the law of composition, that is addition among the vector space, should be just so addition among the vectors in V is just defined in the usual way, pointwise addition, and multiplication by, so this is the law of composition in V. Okay, this one, and then scalar multiplication is just the usual one, right? Is just R times R is any real number. So here this was in V, this was in V, and this is of course in V because R2. I think R2 is at the. We of course say that V is equal to R2, but you know that you know that people also write this brackets in a row. But for us, it will be more standard to use column. Of course, we will sometimes also use row vectors. But anyway, I mean, this doesn't matter. What I want to say is that instead of columns, if you have written them as rows, then also you have the same thing, right? It's just pointwise addition in R. And then R times AV. Here this R is in R, this is in R2, and what you get here, RA, RB, that's also in R2. So in particular, it is closed under scalar multiplication. So now, another example, we saw that over R, this kind of thing, like if you have AB or A plus BI, these are all examples of vector spaces, right? So how about this one? Suppose if you have yeah, please.
So in the first class you said that R2 is not a field.
R2 is not a field, but we are saying that R2 is a vector space. There is a difference between a field and a vector space. A vector space is an abelian group.
Yeah, I understand that, but you showed that it's not a field for some a single multiplication binary.
We are still saying that R2 is not a field.
So
but R2 is a vector space.
But you can simulate complex numbers by R2.
I can simulate
Complex numbers.
Yes. Well, there's a difference between the complex numbers and R2. In complex numbers, you can multiply. In R2,
so I can define a.
You can define. If you define the multiplication in some manner on R2, that is, if your multiplication is not pointwise multiplication, then you can give it a field structure.
So why?
But the usual structure on R2 or any Rn is, when you work on Rn or R2, you work pointwise. Okay? And if you work pointwise, if you multiply the elements in a pointwise manner, then it's not a field.
But why restrict?
And restrict what?
To some specific binary operations.
Well, when you are talking about a field, you are given the field with these two binary operations. Okay? So it's not just if. It's not just a set if. You are given two log compositions on that. So unless you specify which log composition you are talking about, then you cannot say whether you are talking about the field structure or the vector space structure. And for this to consider as field, as you just mentioned, that is, if you take R2 to be, the representation of C as R2, that is coming out to be a field, but not R2, because the multiplication in C is defined in not the manner in which you work on R2. You are not multiplying pointwise, but you multiply A plus BI and C plus BI. When you are multiplying these two, you have something different, right? AC minus BD, right? That is the first thing. Plus I times AD plus BC, right? So you are sending these people, AB and CD, to this one, AC minus BD and AD plus BC. Okay. So, but in general, in R2 or in Rn, we do not even, this kind of thing, that is, you are multiplying two elements in R2 and Rn and getting some element in Rn, that we do not do. We will multiply them. You have seen dot product, I guess, right?
Yes, exactly.
Yes. So you take the map from Rn cross Rn to R, and you multiply actually all of. So if you multiply them, so we rather work with this one and not the multiplication that you see in C, because it's a multiplication field. You are multiplying two elements there, okay, and you are getting an element in field back. Whereas the dot product, we define this as AC plus BD. That is a map from Rn cross Rn to R. Instead of AB and CD, we can have A1, A2 dot A here, B1, B2 dot Bn there. We'll multiply. We'll see. This will come at the end when we talk about inner products. But to answer your question, we do not define the multiplication in R2 in this manner, which sends AB and CD to this one. And then R2 doesn't become a field under the usual pointers. Yes, one.
So actually, I was thinking, like, is there any relationship between multiplication of two complex number and vector cross products, which we learned before?
Yes, as you learned before, so there's little point in again going over that, right?
Okay.
There is. So let's come back to some examples of. Yeah, at first let's consider just the real vector spaces, because that's the easiest kind of vector spaces. So this was what was the last example? C. Yeah. So here we are considering things like, what was C? A plus BI such that A and B are in R. What happens if we replace I by some variable X or T? Is that a vector space? That is, you are considering linear polynomials now. Linear polynomials or constant polynomials, because this A or B could also be 0, right? And if B could be 0, and as well as A. But if A is 0, it's still a linear polynomial. If B is 0, I mean, in that setting where I is replaced by T or X, some variable Z. Okay? So what I'm saying is this, that instead of this, what happens if you consider this kind of things? a plus b x, such that a and b are in R. Is that a vector space?
So what is x?
Some indeterminate, a variable. So this is basically the set of linear polynomials. Are polynomials of degree 1 or 0? I mean, if b is 0, then it's just a constant, right? So question is that whether this forms a vector space B or not. It does, right? Because if you add two linear polynomials, you get another linear polynomial. Okay? So this over R is a vector space. And not only that, you can say that if you have the notation PNR so for polynomials of degree less than equal to n with coefficients from R, this will also form vector space, right? Because if you add two polynomials of degree less than equal to n, you get another polynomial of degree less than equal to n. The additive identity is just 0, right? I'm talking about at first the abelian group structure. The additive identity is 0. Vishesh, you are fine with this?
Yes.
Ashish? So an inverse is just a native of polynomial, right? The additive inverse. Okay, so they form an abelian group. And now if you multiply any element in any polynomial with real coefficients with a real number, you get another polynomial with real coefficients, right? So indeed, multiplication by real number defines the scalar multiplication on this side. Okay, you can check the other, the properties of scalar multiplication quite easily. That is associativity, distributivity, and identity. That is, if you multiply it with 1, you get the same polynomial back.
Can we say about the inverse as well?
Yes. The inverse of a polynomial, we are talking about additive inverse, right?
No, I'm not talking about that. I mean, like you said, V is a vector space,
Yes.
like over R.
Yes. And this
So
is also
can we
vector
say
space
about
over R. We are
Can
talking
we
about.
say R is a vector space over V?
At first, is this a field? There we are talking about inverse statement. In this case, because C is itself a field. But we cannot even talk about inverse here because this is not in a field. Why not? Well, the multiplication of polynomials is defined. So indeed there exists a binary operation which you can know by star, but is the multiplicity inverse there? To have the multiplicity inverse there, what it will require is that a plus bx times some other polynomial, the fx, to be equal to 1. Okay, the user multiplication. Okay. And that means fx would be something like 1 plus 1 by, so fx is 1 by a plus bx. Okay. That's not a polynomial in general. That's, in fact, if you replace this by, so you have seen the series, right? So for example, take one, if this one has 1 minus x, and then the geometric series, so this is the formal series then, and you see that, well, even in its domain of convergence, this is not a polynomial, it's a in fact series. So what we what I mean is that, here is that this one or this one is not a field in general, okay? Because it is the inverse may not exist. It's closed on a multiplication. Sure, it has identity, but the inverse is not there. Okay? So it's not a field, and therefore flipping the question doesn't make sense here. All right. So now we, if you recall, when you wrote down the syllabus, vector space came second compared to this. Okay. So first one was solutions. No, opposite. I didn't mean for you to see there. I just wanted to write down here. So this was 1, 2, and this 3. Because if somebody else comes and writes their name there, then it will be disturbed for you. So we just considered polynomials, and then we said that when we wrote down the syllabus, there was something before that, that is linear equations, right? Linear equations and matrices, which we skipped because we did something like something on linear equations and matrices, matrix manipulations, etc. in the previous semester. But now consider these the solutions of, let's say. Okay, at first, you are given a matrix A, and n cross a matrix over real entities, or it is in some field, and then consider the system of linear equations Ax equal to 0. That is the system of homogeneous linear equations. And suppose V be the set of all x's in Rn such that Ax is equal to 0. Okay? So all n cross 1 vectors, you multiply with A and you get 0. Okay? The system of homogeneous equation of this form. Okay? The question is that whether this is a vector space over R.
Yes.
It is, right? Because if y satisfies the same equation, so suppose let x and y. So now there comes this point where you are asked to check whether a given set is a vector space. Okay? And how do you check that? We do this in this manner. Let xy be in V. Then we consider whether ax plus by is in V or a b in F. Okay. Well, we are considering R here, so R a b in the field of real numbers. Note that if this is so, then in one go, which are the things that we have? Well, in particular, it says that x plus y is there in V, right? What else? You can choose A and B to be zeros. Okay. So that would mean that 0 is also in V. Okay. Identity is also done. So, the law of composition and identity both are done. And then about the inverse, you can choose this one as -1, this one as -1. Okay. That is the additive inverse of the multiply divided, -1. Right. That would mean that you have to do some basic works there. That is, these are indeed giving you the right things. So you have to get that this is x, -1 of the field times x plus y is indeed the element of which will invert x plus y. But these are easy exercises, and you can check these ones just from the definition of the vector space. So what we want to say is that here, if you have this condition, in one go it checks lots of things. At first, that V is an abelian group, that scalar multiplication is defined. Only the few things which are left to check are the properties of the scalar multiplication. But that will follow easily from these ones. If you have Ax plus By in V for all A and all B in V. So usually, checking this in particular for subspaces, if you are given a vector space, well, we come to the definition of the vector space of subspace in a moment. But let's check this and then see what we have from this condition. And this is kind of obvious, you see, because if x and y are in V, that means that x is equal to 0, a y is equal to 0, and that a times y is equal to 0. So that in particular would mean that our required expression is also in V. So you have ax equal to 0, ay equal to 0 as x and y are in V. Okay, this set, and this has a name. It is called either the solution space of the homogeneous equation ax equal to 0, or it has a short name that is called null space of A. Okay, so that's the name of the space. It just means null space of A is the solution space of the homogeneous state of homogeneous equations given by ax equal to 0. Okay. And since x, y, and v, then these two are true, and that would imply that a times ax plus by, this is equal to a times ax plus b times ay, which is equal to 0. Okay. So of course, ax plus by is also giving a solution to the homogeneous equation. It should also be in V. Okay. Ax plus by is also in V. In particular, it's an abelian group. There is scalar multiplication. And about the scalar multiplication, what are the things that we should check? One is the identity thing, right? So, yeah, and that would mean that, well, we don't even have to check that, because there is a well-defined scalar multiplication on the set of the, what you call? Well, we are considering x in Rn, right? And Rn is itself a vector space. So on Rn, scalar multiplication is well defined. Okay? And now we are just in a subspace of Rn. That is a null space of some given matrix A. Okay? So if you are in a subspace, the properties of scalar multiplication is already given to you. Okay? That it is satisfying these three criteria: associativity, identity, and distributivity. So all you have to check is this one. Okay? So if you are proving that a space, so if you are asked to prove whether V is a vector space, and you can already see that V is a subspace of some space which is already, on which there is already well-defined scalar multiplication, then all you need to check is just whether H plus Vy is in V for any A and any B from the field. That's all. Let's write down formally the definition of a subspace. Vector space. Okay. So we call W a subspace of V if first thing is that W in V is an abelian subgroup. Now, what does it mean? It's a group under the same law of equation as in V. So V plus, that is here plus was the group law, and under the same group law, W plus is also an abelian group. It's closed under addition, I mean the binary operation defined by addition, and it satisfies the group of properties. That is 0. Yeah.
And we call every vector space a subspace.
Every vector space a subspace. Oh, every vector space is a subspace of itself. Okay. Yeah. So this is an abelian subgroup, and 2 is that W is closed under scalar multiplication on V. So suppose V is a vector space over some underlying field A. Yeah.
And you repeat what a subgroup is.
Yeah, sure. It's okay. So yeah, it's quite simple to understand. It's W itself is an abelian group under the same law, which is law of operation as in V. Okay, and it's a subset of V. So it's a subset which is closed under the same law of composition as in V, and it satisfies the two properties. Okay, so not only closure under the binary operation, but it should also have the identity, the same identity that as of V. So 0 should belong here. Okay, and for every element in W, its inverse should also be in W. Okay. So it's an abelian group in the proper sense with the same law of composition as that of V. And the second thing is that W is closed under scalar multiplication by elements of X. By the elements of X. Okay. So instead of checking these two properties one after another, you can just take two elements of W and take a linear combination of them and check that whether that linear combination is in your subspace W. In order to get that W is a subspace, you just have to ensure that a thing like that, A times some element of W, so let's write it down here. These two properties would easily be verified if you just show that these two properties is these two properties are verified if for all A, B in F and V1 or sorry W1, W2 in W, we have AW1 plus BW2 in W. So this is the only thing that you have to ensure to show that a given set or a given subset of V is indeed a subspace of V. Which one here now? Maybe this one. And now, well, take it with the last example before we move on to something else. So, let if, well, let's consider the functions. Which satisfy the differential equation, say if W dash equal to minus A. So consider the set of functions let P set of functions from R to R, say would satisfy this equation. Okay. Then note that they form a real vector space. You can add F and G, any linear combination of F and G. Well, again, here also to show that this indeed forms a vector space. What you have to show? Yes. So some A, F plus or F and G in V, AF plus BG is also in V. And why this surfaces? This will surface if you can say that V is subspace of another vector space and well-defined vector space on R, on which the scalar will satisfy this properties already. That is an abelian group under the same addition like this, and the scalar multiplication is also well-defined on that. So once you embed V into such a superspace, then it's just fine to check such linear relations. Right? So at first you have to give justification that we are going to show that V is a subspace of what? Set of all relevant functions. The set of all functions from R to R. Thank you. Your name, please? Yeah. Zinedine. Thank you. How do you pronounce it? Zinedine or Zinedine? You end with the N. So yeah, and this is rather trivial because I mean from the properties of differentiation, right? So you differentiate this entire thing twice, and you get A F double dash B G double dash, right? And F double dash you know that is minus F. G double dash you know it is minus. So A F double dash plus B G double dash should be minus F minus BG. So this will also satisfy this equation. Well, we are assuming that we are going to show that V is a subspace of the set of all functions from R to R. But nevertheless, here we are assuming that the scalar multiplication is well defined on this. And this is actually, I will multiply any, so it is taking some real value. Okay. At first, if there is a function f, then minus f is also a function there. If f and g are two functions, f plus g is also a function from R to R. Okay. And scalar multiplication, the usual properties, the associativity, identity, distributivity, all should be satisfied here. So, if you already have a superspace like this, then for a subspace, just this one will satisfy. Yes, two people.
How do you know that only f and g are the functions which satisfy this?
I don't know whether f and g are these are two arbitrary functions. So for any function f and g,
how do you know there are only two functions?
I am not saying that there are only two functions. I am saying that for all the functions, for all f and g in V, the linear combinations of them of this form a plus bg is also in V. Okay. And we are saying that showing this would suffice to show these two properties. That is, this is an abelian subgroup and this is closed under scalar multiplication. So, Shukrit, please don't nod if things are not clear. So again, I want to understand the root cause of the confusion. I never told that f and g are the only functions. So why are you confused? I think I'm missing something here. So please let me know what you're missing. So again, what is the exact doubt? Please tell me. So where are you confused? The definition of subspace or? I doubt it. Otherwise you shouldn't have asked this. I'm not barring you from asking questions, but unless it's completely clear, keep on asking. Okay? And it's true for all of you. If you are stuck anywhere, yes.
The function f double dash is minus f.
F double dash.
is equal to minus A.
Yes.
Like for this subspace, only this one is like, if we prove this one, all the other functions are also true. Like there may be other functions which is not satisfied.
Other
Functions from R to R.
Yes.
Which may not hold true.
Yes, and those are then not in V. So V is a set of all the functions which satisfy this differential equation. Okay, all of which satisfy.
For this particular function, V is defined.
Yes, not for this particular function. It's not a single function. It's a differential equation. This one just means that we are defining V to be the set of all functions from R to R such that the 2f, call it a function of t or x, t is fine, d2f dt2 is equal to minus. So it is a set of all functions which satisfy this differential equation. Okay. Just earlier we were talking about system of linear equations, null space given matrix A. So now instead of talking about a set of linear equations, we are talking about a set of differential equations. Okay. And instead of talking about just a set of subset of Rn, now we are talking about a set of functions. Okay. And put it there, then we are assuming that f and g are two elements in V. Okay. And what we are trying to show is that if f and g are in V, then for all a, b in R, we have af plus bg is in V. Okay. And now see whether this is, I could understand, one point could be that I was just talking but I was not writing down the entire thing. So that might confuse you. But after we wrote down everything, is there anything that still bothers you? It's not ideal. So anybody else? I mean, if you have any doubts regarding this, why it's a vector space or what we are exactly checking is.
It's clear that it's a vector space. My question was that can we solve for this kind of question? Will it be helpful for us if we solve?
It will be helpful for us, but we are not going into that at the moment. At the moment, we are just considering the thing that whether this is a vector space or not. Okay. So later we'll see that how to generate spaces of such things, whether there exists a canonical solution or a set of canonical solutions. But at the moment, we just thinking about whether this is a vector space or not. What is the structure of solutions of this? Okay. And the structure of solution space is a vector space over R.
So how are you saying that taking linear combination will satisfy those two?
Yes, alright. So taking linear combinations means that you are having all such A and B, right? So at first choose A and B to be 1. So 1 in the field. You know that 1 times F is F itself, right? 1 times G is G itself. So F and G is there, that means F plus G is also there. Okay. So if you get any linear combination, then you get that in particular F plus G. So this is closed under addition in the vector space. Alright. Excuse me. Could you just what's your name, please? No problem. But I'm just trying to figure out whether you missed anything from the class. So we are trying to explain. Again, your name is Shubhadu. Yes. And yours? Yours? Yours. No. Who asked the question? Yeah. Rahul. Okay. So we are trying to answer Rahul's question. That is, why A plus BG in V implies that both of these are satisfied. So this is actually a thing that you should not miss, because you may be asked to show that given a set, show that this is a subspace of V. Okay? It's an easy question once you understand how to do this. Okay? And we said that it will suffice if you just take a linear combination like this, A times F plus B times G, with A and B from the given field, and show that this is inside. And we just said that if you take A and B to be equal to 1, that would mean that f plus g is in V. So it is closed under addition. Okay? And the next thing that we have to show is that the inverse exists. Take these to be the negative of 1. Okay? Because if 1 is there in the field, minus 1 should also be there in the field. It's a field. In particular, it's an abelian group. So additive inverse. Sorry. Yes, that is the additive inverse of the multiplicative identity. 1 is the multiplicative identity. Take the additive inverse of that, you get minus 1. Minus 1 times f. It's rather simple to check. If 1 times f is f, then minus 1 times f is also something, also equal to minus f. Okay. And so, in particular, taking this equal to minus 1, this equal to 0, you get that minus f is also inside this. So, identity and inverse is done. Okay. Scalar multiplication should also be done because put any of them to be 0. Okay. Then f inside V, that will mean AF is inside V for all A. The scalar multiplication is also done. Okay. And since it's a subspace, you don't have to check the properties of scalar multiplication by hand, that is, whether it satisfies associativity, identity, or distributivity, because it is a subspace. In the original space, the scalar multiplication is already defined. All you have to check is that whether it is closed under scalar multiplication. That is already checked by this. So that's why checking this condition will, I mean, in one go you are checking both of these conditions. Okay. Rahul? Surely is not here. So now it is, we have a class or lab after this.
No class.
Class? Okay. And I said that before coming to my class, you can ask for leave. 5 minutes.
There is no class.
But you said that some of you have classes. So please raise your hands. How many of you have classes now? Great. So at least we can define what is linear. We just said talked about this as linear combination, right? The next thing that we can define, I think we should define this before. It's as you mentioned, tomorrow is Independence Day, so let's define at least linear independence. Okay. So yeah.
Sir, how do you know that V
Yes.
is a subspace of all the functions?
The subspace of, okay, so V is a subspace of all the functions. Well, V is in particular a set of functions, right? So V is a subset of the set of functions. It's a subset. It's inside the all the elements here are functions in particular.
Or picking up functions from the all the functions and then we are applying it.
Yes. So suppose this is suppose we have a pool of all the functions from 1 to R, and you are just taking out the functions from those which are satisfying this.
We are defining it to be the subset.
Yes, we are defining it to be the subset, to be the subset, and then we are showing that it is indeed a subspace because all such linear combinations are there.
So not all subsets are not.
All subsets are not subspaces. Okay.
Sir?
Yeah.
But before we proceed to the closure on the addition and square multiplication, so we have to prove that B is a space itself.
V is a?
Space itself.
Yes. I mean, just discuss this when we wrote it down. We didn't write down clearly why it's a space. But suppose you have a function from 1 to R, multiply it with any real number, you get some other function from 1 to R, right? Add to such, f and g, which are functions from 1 to R. F plus g is also a function from 1 to R, okay? And yeah, so what I want to say is that, indeed, if you are saying that it's a subspace of some space, unless it is, unless the conditions are already verified there, you should also check the conditions there. That's true. Okay. And checking for the conditions for this, the set of all functions from 1 to R is very simple. Yeah.
So here it's a simple differential equation, and we know there is a solution. So if we don't know, without
even if we don't know, well, at first you have to show that there exists some solution. Yeah. And if well, at first check that whether 0 satisfies this, because you need the anti-binary there. Okay. And if 0 is there, 0 is satisfying this, then your space is not empty. So then, your space has at least one element 0. Okay. And you can, then this definition goes on. So in particular, if you have a homogeneous system of differential equation, there's no problem at all. 0 satisfies that always. Alright, and yeah, so just to complete this, A plus BG double dash is equal to minus A plus BG by definition of differentiability. And let's just define formally what is a subspace to define, what is a linear combination, a linear relation, and linear independence. It will take 5 minutes. So at first, linear relation not even linear relation, at first linear combination. Of vectors v1, v2, vn in some vector space V. Okay? By a linear combination of vectors, what do we mean? C1 v1 plus C2 v2 plus plus Cn vn, where Ci's are from the field. So this vector space P, there is always of course an underlying field from where the scalar multiplication will be defined. Okay, and all such, so a linear combination is just such a thing where all the coefficients are coming from the field. Like here we said that this is a linear combination A plus BG. In general, if you are given n vectors, such a thing C1 v1 plus Cn vn should be called a linear combination of v1 to vn. Okay? And then we say that there exists a linear relation among v1 to vn if there exists, well, for linear relations you do not have any constraint on the coefficients here. So by linear relation we mean, just a minute, let me write it down here. So by a linear relation, what do we mean? A relation of this form, C1 v1 C2 v2 plus plus Cn vn. So some linear combination which is giving 0 as an output. Okay, 0 in vector space. So this is a linear relation of or among the vectors And now,
sir,
yes,
instead of
and this, of course, this all these CIs are in A. Yes. Issues?
none.
So we are going to define linear independence in a moment, but before that, let's note this. That is, given such, given C1, C2, Cn, and v1, v2 to vn, such a thing would be called a linear combination. Now, suppose you are given this vector v1, v2 to vn, and you take the set of all linear combinations of them. That is called the span of these vectors v1, v2 to vn. Okay? So let's define it here already. A span of v1 vn is the set of all linear combinations of v1, v2, vn. Okay? This is called the span of v1, v2 to vn. This would be, so at least till this course done, this definition of span would be very important. So do not miss it. Okay? Span is quite simple to understand. It's a set of all linear combinations. Okay? Okay? And then the next thing that we are going to define, this is also a rather important thing. And throughout the course, we will use these terms span and linear independence. Okay. So please pay attention to this. Linear independence of linear independence. The set of vectors beyond order Vn in V is called linearly independent set of vectors. Linearly independent if the only linear relation among V1, V2 to Vn is 0 times V1 plus 0 times V2 plus whatever plus 0 times Vn equal to 0. So the only linear relation is trivial. Okay. That means if you have such a thing, such a linear relation, all of these coefficients are bound to be 0. If that is true for a set of vectors V1, V2 to Vn, we say that this set V1, V2 to Vn, if such a thing happens, then this set V1 over Vn is called a linearly independent set. In other words, the opposite is that is when you call the set linearly dependent, when such a relation exists with not all of them to be 0, we call the set to be linearly dependent.
Not all at the same time.
Not all zeros at the same time. All of them are simultaneously 0. That is, see, you have a linear combination like this, okay, which is giving you 0, such that at least one of the coefficients is not 0. Yes.
Sir, can we take N as 1 and still define linear dependence?
Of course, yes. That's a very good question. Thank you, Rishi. So, in particular, suppose the set is just having one element, U1. Okay. Then what would it mean by the set to be linearly independent? That is, the only relation C1 V1, which is equal to 0, must have C1 itself equal to 0. What does it mean?
Non-zero vector.
All the non-zero vectors, right? Take any non-zero vector that defines a linearly independent set. Okay? Now, related to that, such a set can it have 0 as a subvector? That is, can it say, for example, Vn be 0? Why not? Yes. So you can take all the other coefficients to be 0, and since this is 0, you can take this to be whatever you wish. And that's not allowed if the set is linearly independent. Right? So 0 cannot be an element in a linearly independent set.
So why aren't you mentioning that?
It doesn't, we do not require to mention it. It is following from the definition, as we saw.
So we can still consider one of the vectors 0, right?
No, we cannot. In a linearly independent, when we are defining linear independence,
Consider that.
we say that this is the only linear relation among them. Now, if your V1, for example, or Vn is equal to 0, then this is not the only relation among them. You can take its coefficient to whatever you wish, and you will still get 0 on the right hand side. So that's all for today's class. Thank you, and see you on Monday. All the best for the exam today. It's just on matrices.